Dr. Ravindra Duddu got his Bachelor of Technology from IIT Madras, then his MS and PhD in Civil and Environmental Engineering from Northwestern University. And after that, he worked as a postdoc at UT Austin and Columbia University. And currently, he is an associate professor at Vanderbilt. And Dr. Duddu's research interests are in computational solid mechanics with a focus on multi-physics modeling of material damage evolution, with application involving fracture of Antarctic glaciers and ice shelves, fracture and fatigue of composite materials, and corrosion of metal alloys. He received an career award and Fulbright Climate Fellowship and a UK Royal Society International Exchange Award and ONR Summer Fellowship. So currently he's the chair of the Computational Mechanics Institute in EMI, and also the chair of the Fracture and Failure Mechanics Committee in SME. So without further ado, let's welcome Professor Duddu.
Yeah, thanks everyone. It's really an honor to be here with you all today, so thank you for joining me. On Wednesday night I was fine, and Thursday morning I lost my voice. So I'll do my best to be as loud as possible. Usually that's easy for me to be loud. Today it's challenging. Let me begin by saying thank you to Jialiang, Kaichi, and Stefano, and for inviting me, for being my friends through good times and also some bad times sometimes. So as Jialiang said, I'm an associate professor at Vanderbilt University. I've been working with phase field fracture models since 2020, so not not too distant past. And so I want to give a few updates on what we have done and how we are using it in applications. So before I begin, my lab name is Computational Physics and Mechanics Lab. So when I first joined the civil engineering department at Vanderbilt, they said there's no civil or engineering in your lab title, and I said that's really how it should be. There's no engineering in National Science Foundation, but it funds a lot of engineering work, right? The basis of any engineering has to be grounded in physics and mechanics, and with that as our motivation, so we aspire to model and predict material degradation, and two applications that we are interested in are fracture and corrosion. And corrosion slowly became an interest in electrochemistry and electrochemical processes, which we are expanding into. It involves mechanical, thermal, and chemical phenomena, and we have to model all these together in a unified manner. And so that brings in the interdisciplinary aspects, engineering mechanics, applied mathematics, material science, earth science, and scientific computing all together. We mainly operate in this mathematical and computational modeling space. We work with a lot of experimentalists and observational people. And part of the reason why I go to conferences and come and give talks is to make more collaborations with experimentalists. And so would love to chat with some of you if you have some time later. We build advanced models when we want to understand new material behavior, but we also try to develop robust methods to simulate material behavior. I'm mainly going to focus on this part in today's talk. How do we develop better methods to do large-scale problems? I want to acknowledge with all the funding agencies that as of today still operate. So NSF, maybe some of you got the joke. So NSF funded this through the Arctic and Antarctic Sciences Program. So we are very fortunate to have received their funding and also career from the Office of Polar Programs. NASA funded us on some of the ice shelf work. Vanderbilt, the Royal Society, the Fulbright Fellowship was from the USIEF Foundation. And last year I was here in Minnesota to visit 3M campus because they were funding us on some of the work. I'll talk about it a little bit later. And very recently we received funding from Heising-Simons Foundation to do AI-based prediction of ice sheet fracture. And all the various postdocs and grad students that worked with me at Vanderbilt, and undergrads and high school students who always have the passion to learn new things. So I want to acknowledge all their contributions and all the several faculty and staff that helped collaborate with us on these projects. So a few applications. Mainly we work on these Antarctic ice shelves. So we use damage mechanics models to predict how icebergs calve off big Antarctic ice shelves. And this is a very, very significant result where we were able to match the exact calving pattern which is found in real ice shelf. This is a Larsen C ice shelf in Antarctic Peninsula. We were able to match it with simple damage mechanics models. So that's where our NASA funding supported us. We also work with delamination problems and woven composites funded by ONR. I didn't acknowledge them earlier. And then we are also interested in brittle fracture of rocks going towards sometimes hydraulic fracture and sometimes maybe just simply like how do rocks fracture. So a lot of our work is grounded in the fracture physics or fracture mechanics. So I want to maybe just focus only on a part of the thing about computational fracture mechanics, how that field evolved. And I won't be mentioning all the contributions by all the people in fracture mechanics. So please bear with me with the limited references. One of the first papers that I read when I was a student was Alfano and Chris Field's paper where they classify all the computational fracture mechanics approaches into two classes. So one is this linear elastic fracture mechanics approaches. And the first methods were done by a few people at NASA, and then Irvin and Ribicki and Raju and all these folks, maybe through the Naval Research Lab, and they started working on this virtual crack closure technique. So they use a numerical way of calculating stress intensity factor, and then they use that to propagate cracks in finite element method. Then came the integral methods where Professor Jim Rice and others and Moran, who was my PhD advisor at Northwestern, and then Bob Dodds at Illinois, all of them started working with these J-integral methods. And that is incorporated into Abacus, for example. If you do any fracture propagation, you would probably use a J-integral. And then came meshless methods, XFEM. So Professor Belichko, who taught me finite elements at Northwestern, he coined the term XFEM. Professor Winkham Liu did a lot of work on meshless methods, again at Northwestern. Professor J.S. Chen, Armando Duarte at Illinois, they all were improved GFEM, XFEM. And honestly, like the GFEM, XFEM come from partition of unity methods. So a lot of folks like Babushka, who I met when I was a postdoc at UT Austin, and many others there contributed to the early foundations of it. Then there are continuum damage mechanics methods, which is the other class. And the difference between LEFM is that it assumes cracks are sharp. Continuum damage mechanics assumes that the cracks are diffused. And also, it's not modeling sometimes just one crack. It's modeling a collection of cracks, right? So there is one way of interpreting continuum damage mechanics is that there is one crack, but you're thinking of it as a diffused crack. And the other way is thinking there are many, many small cracks, and you're modeling it as one diffused damage zone. So when Kachanov and Mazars, they formulated their original damage mechanics models, they thought it as, materials don't fracture with one crack. They have multiple cracks before a macro crack forms, so you should model them as damage zones. And then came the non-local gradient-based approaches, because local damage approaches that Kachanov and Murakami proposed, they did not satisfy thermodynamic requirements when you're doing modeling. And so Professor Bajant, who's Jialiang's advisor and also my teacher at Northwestern, they came up with non-local integral approaches to account for that fact that you need to make it thermodynamically consistent. And then DeBourse and Professor George Voyages and all contributed to gradient-based approaches. And then there were whole different cohesive zone models. I won't go into the details of it. Several researchers contributed to it in the past. They assume this zero thickness cracks, but they have a length scale, right? And so it still falls into the continuum damage mechanics. Its cohesive zone models are not, they connect in some way the LEFM to the CDM with the concepts of, strain energy release rate and so forth. But as Alfano and Crisfield argue, it's still a CDM-based method. Some people may disagree on that, but we can chat. So now this phase field method comes along. It's been proposed by Frankfurt and Merigo, and then Blaise Borden, and several other researchers did early work. And then really in 2010, when Christian Mihei started to work on these in framing them, that's when the community started adopting this in computational fracture mechanics. And there are still arguments to be made. Is it a non-local damage type approach, or is it some sort of a diffused fracture mechanics approach? And so I won't go into the debate today in the interest of time, but I'm going to think of this as a non-local damage approach in the way I present it. And other methods like peridynamics, crack band method, discrete and particle methods, they all exist. They're useful in many, many ways, but I won't go into that into the interest of time. So that's sort of the history of computational fracture mechanics. The outline of my talk is just presenting a few of my recent work. So part one, I'll try to quickly present what we did in these two papers, and then march forward with the other parts on experimental calibration and also how to apply machine learning in this context. So our phase field fracture modeling was motivated by these huge fractures that appear on Antarctic ice shelves. And in the glaciology community, they classify these fractures as crevasses and rifts. So when you go to a glacier, this glacier is about maybe 100 meters in height, okay? So that's huge, right? So think about multiply by 3 if you're American, that gives you feet, right? So it's 300 feet. So vertical fractures that go almost more than half their thickness. That means these are fractures that are about 50 meters, 100 meters deep. So the original motivation for studying these fractures is that if there was a field expert somewhere, hopefully not, if someone was doing something, they could fall, that's it, right? In fact, there was a death in one of our glaciologists, very famous ex-field glaciologist who passed away 2 years ago, falling in a 10-meter or 20-meter crevasse, and it's very hard to detect them. So the motivation was early to understand why crevasses form, where they form, so that we can make field exploration a little bit safe. Then climate change starts to take off. We have these crevasses going full depth and then forming these huge rifts, which are hundreds of kilometers long and then you have icebergs coming out of Antarctica that are size of the state of Delaware, right? And nobody has probably been to Delaware, like I've never been to, so we don't know. So it's the entire metro area of London, if that's a better estimate for you. So these huge rifts are formed by these crevasses. Till now, there are no models in the glaciology world where you can take a fracture initiation problem, go to crevasses, and from crevasses you go to rifts, and do a whole 3D fracture representation in a unified manner. So in 2010, as a postdoc, I started on that problem, and for 13 years, I've been solving this, and finally we have made some headway, right? So these are challenging problems. And that's because there is creep deformation, there is material state and damage evolution, there is thermomechanics, all that involved in this. So the phase field model presents a unique opportunity to model these sort of processes because it's very compatible with finite element method, and it's thermodynamically based on the Griffith's theory of fracture, which goes back all the way to 1921. And it naturally evolves fractures through initiation, propagation in 2D, 3D, and that gives us a holistic way of understanding these processes. So to simply explain how this energy balanced approach or energy balance approach works, you first define this potential energy stored within the body. There are two parts. One part is the strain energy, right? So think about a body like a spring. When you extend or compress the spring, there is deformation in the spring that stores potential energy, correct? Kx squared. And so in elastic bodies, you have the strain energy release rate that stores this, the strain energy stores this body. But when fractures happen, two new surfaces are created, right? The top and bottom surface of the fracture, and that decreases the energy stored in terms of the strain energy. So the combination of the both should give you conservation, right? So that's what this equation means. So the sum of the strain energy stored in the body and the strain energy, the energy for fracture, they both have to be balanced. If you try to minimize this, because what the idea is that whenever a fracture surface is formed, what it's trying to do is it's trying to minimize the stored energy, go to energy minimum state. You can minimize this for two primary variables, the damage, the phase field damage, and the displacement that governs the strain in the body. And you get the equilibrium equation with the effect of damage. So this is the divergence of the stress field, and assuming it's quasi-static. And then the next equation that you get is the phase field evolution equation, which has this Laplacian term with the L, which is the length scale defining the diffused zone thickness of the damage, right? So that's how I understand it in the simplest way possible. There are many more interpretations on this with more advanced models. But this is the basic model that we'll operate with. So we take that same phase field evolution equation, we can add some viscous regularization for avoiding certain numerical issues. And that is how we started in our first paper in 2021 during COVID, and we published it in 2021, where we started with the crack driving force as the positive part of the strain energy. And the understanding here was that when cracks grow, they grow in tension, not in compression, right? Brittle fracture. But when we started with only that, we were getting fractures everywhere, even in compressive zones, even though we said this positive part is only based on the positive eigenvalues of the strain. And then we dug deeper into it. We looked at Chad Landis and his students' paper, Yusheng Lo, and they pointed at this a few years ago in 2019 that if you take the strain energy function like this, which is based on two positive strains, then you are only modeling this region where the strain energy is rapidly growing with the strains. But in plane strain systems, you can have one strain positive and one strain negative, right? So you can have tension in one direction, but compression in the other direction due to the Poisson effect. And when that happens, if you don't correct this strain energy to a different form, then you're overestimating the strain energy and you're over-predicting the fracture. And so you need to model regions 2 based on this when one strain is positive but the other strain is negative. So if you see 0, right? So this strain is, let's say, negative, but this strain is positive, and in that region it has a different slope. And then in regions where the 1 and 2 both are negative, then you have to have the strain energy 0. That means it cannot propagate in compression. So when we apply this model, you can see for a simple problem in glaciers, and I'll come to the boundary conditions a little bit later, what you have is that the stress, sort of like bending, goes from tension in the top regions to compression in the bottom regions. And if you take the standard Meehay model, you get positive strain energy everywhere. That means all the fractures grow everywhere. But if you take this Yu-Sheng-Lo model, they only grow in the top regions. And as I showed you the picture of crevasses, they only grow in the top, right? They're always opening up at the top and growing to the bottom. And so only the Low model seems to explain this based on the understanding of the problem and also matches with field observations. So this was our main contribution of that first paper. And then I connected with one of my collaborators, Emilio Martinez-Pineda, now at Oxford. And we started working with his student and said, if fractures are driven by positive stress regions, then why go through all the strain energy-based models? Why don't we go to stress-based models? And then we simplified this phase field model. We got rid of the viscous term. And then for the crack driving force, instead of defining it based on strain energy, now we write it in terms of the positive principal stresses, right? So sigma 1 is the max principal stress. I should say sigma 1 are the principal stresses, and anytime it's positive, so Macaulay brackets, right? Then we add it into the crack driving force. We apply a threshold for crack growth, and then you get this formulation. And this surprisingly also works for incompressibility. If you're doing soft materials, it works good as opposed to the regular model. If you're doing brittle tension compression asymmetric materials, it works better. And we have also been able to adopt it into hydrofracture type settings. So how do our results look? This is a paper that we wrote in Engineering Fracture Mechanics 2022. So we take this glacier problem. We have a small crack at the top. Engineers, right? We put roller boundary conditions on top and bottom. There are no roller boundaries in real glaciers. It's not even rectangle, right? But the domain was inspired to then compare with LEFM, the analytical models. So you have ocean pressure on the right-hand side trying to stabilize the crack process here. And as you can see, the cracks start from this notch and they propagate and then they grow and stop. As soon as the compression, it goes into the compression region, it stops because no longer there is driving force. And then we derived a linear elastic fracture mechanics solution. In the appendix of this paper, you can find the whole derivation. And the lines are the linear elastic fracture mechanics analytical solution. These little round circles are one simulation each in phase field. So what we do is we choose a certain level of water in the cracks and a certain height of ocean water. And so we have 3 ocean water heights, several different meltwater heights in the crack. And then we are doing a parametric study. And and every point our phase field model agrees with linear elastic fracture mechanics. So then we said that this sort of verifies that we are doing good, right? So for this, we do some sort of adaptive finite element method. We use quadrilateral elements. We use COMSOL in this case. We can do multiple cracks. And for multiple cracks, we can again get the corresponding LEFM solution, because when there are multiple cracks together, there is crack shielding, right? So then the stress intensity factor is actually lessened by it. And so you get smaller crevasse depths. And then we compare that with phase field, we get good matching even in that case. And in real glaciers, as you saw in that picture, there are cracks at regular periodic intervals, right? And that's because there's always some driving stress where once this cracks goes deep enough, it's no longer favorable to grow here, it's favorable to grow there. It's favorable to grow there, right? And so you have partial depth cracks growing in this nice periodic fashion. And then we started trying to do the 3D problem, right? As I said, there's no model that exists where we can go from 2D to 3D and understand iceberg calving, where the rifts fully form and separate icebergs. So we considered a simple problem. We took a rectangular shaped 3D glacier. We put the same ocean boundary condition. We took 2 cracks on each side, and we put the ocean water height as half the ice depth. And we, hopefully the movie will run again. Yeah, so we saw that crevasses immediately form, they go below, and then they start propagating in plane. And then they start connecting, and they form huge rifts. But because there is the ocean pressure, they don't go all the way down. So that means in this case, there won't be a separation of icebergs. They'll propagate, and they'll just stay dormant. But once you put a lot of hydrofracture, a lot of water into those cracks, then they start propagating, and then you get full fracture. So what we found out through this work is hydrofracture is an essential component of these iceberg calving processes. If you don't consider that, you don't get it. And it's not hydrofracture like how we do it in oil and natural gas exploration. So it's not dynamic, like it's not turbulent fluid flow. It's just slow water-based fracture that happens because water has a higher density than ice. So it applies a little bit of pressure, more than the closing ice pressure, enough to slowly propagate this crack over time. So all those things, all those critical insights can be obtained through modeling, right? So this is where we hit a hurdle. This simulation, as simple as it looks, ran for 7 days in COMSOL with 4 cores or something in parallel on the computer at Imperial College. We couldn't run many simulations like this. So then we said we need efficient methods, right? So then we started exploring with some collaborators at Durham University. This is through the Royal Society's International Exchanges Award. We started looking into discontinuous Galerkin methods. How many of you have studied finite elements? But in finite elements, you use continuous Galerkin, the Lagrange shape functions and all those. But you can also try to make them discontinuous. And when you do that, you make mesh refinement very easy. Each element has its own support. You can just partition the mesh elements. You can have hanging nodes, no problem. But you enforce continuity using weak form implementations. Okay? I won't go into too much detail. But when you do that, you get very nice adaptivity with hanging nodes. You can use polynomial refinement. You can do mesh refinement, mesh size refinement. You can parallelize them. But it's also complex and algorithmically, and it's computationally costly. And just to show how we can model a fracture problem, as the fracture is going, you can adaptively refine the elements only in the region where the cracks are growing in both polynomial order and also mesh size. So in fact, in this case, we use 6th order polynomials in certain regions to reduce the mesh size. So you can get efficiency if you do it right. So that was a paper we wrote in CompMex, and Robert Bird, who's a postdoc at Durham, led this work. I was not leading this work, but collaborating. On the other hand, we were leading at Vanderbilt on adaptive methods in Phoenix, which is the open source finite element software. And there, we wrote a few papers in the last few years from 2022 with my postdoc, Abhinav Gupta, and my grad student, Nguyen, T.N. Nguyen. And this is how it works. So you take a rectangular ice shelf or rectangular block, doesn't matter, and you start propagating a fracture. You only refine it in the region where it is the crack tip, and then you propagate. You didn't refine anything in the far field, so you're introducing degrees of freedom only where it's necessary. And you get a very nice fracture path because it's mode 1, right? The easiest problem to solve in fracture mechanics. But we do that in this 4-step stage of refinement. So we first take the crack tip, we look at the strain energy increment from one time step to another. We then mark that high strain rate increments for refinement, and then we see what is the actual strain energy. If it's not so high, then we unmark, and then we look at the damage variable, and we say if the gradients of the damage variable are very high, you again mark them for refinement. And then if you hit a certain level of refinement, we don't want to over-refine and make it too computationally expensive, so you again unmark them. So we go this 4-step process, we get a very optimized mesh, and that's how we drive this crack tip refinement. And so now we are able to solve sort of real crevasse problems in 3D, and so we can solve these both scenarios where there are multiple cracks in a 3D ice shelf that are growing, coalescing, and some don't. And you get these real crevasse fields that look like crevasses in the field. And we solved this for 17 million degrees of freedom on just 40 cores. And this ran for less than 5 hours, right? So we are able to deploy it in parallel. We are able to scale it to multiple processors. We use algebraic multi-grid preconditioners and iterative solvers in PETSI to then drive the efficiency in cracks. We can also do isolated crevasses, and then they grow like these individual rifts. They go all the way. But when you have multiple crevasses close by, some will get shielded, right? So not all crevasses will propagate. So we can understand these sorts of settings, and we can make hypotheses, right? So the hypothesis we made is that there is some sort of connection between the geometric and material properties of ice, where there is a characteristic spacing that comes out of this competition between the driving stress and the material strength. And that's what we want to find out next and match it with field observations. So that's part 1. And then I'll try to skip a lot of the experimental calibration aspects quickly in the interest of time. And so Purdue came up with a damage mechanics challenge. They did 3-point bend experiments on 3D printed rock because they can, right? So they have fancy equipment. They can take gypsum and they 3D printed rock. And then they did standard 3-point bend tests, which a lot of you know. And they gave us the load displacement curves, and they also gave us the peak strengths of it. And the whole data set is given here. They also did DIC. They also did X-ray tomography to get fracture surfaces and all. So it's a very, very extensive data set. So this is the data that came out. They did one test where they put a notch here at some eccentricity. They gave us 3 experimental data for each. There was one experiment that didn't go well, so they asked us to disregard it, right? So they did 4, but 1 they threw it away. Same thing, right? Another test, slightly moved notch, and then another one, they put the notch at an inclined angle like that, and another one, they put it right under the load, right? Like a standard 3-point bed experiment. In all cases, we got the load displacement diagrams. And they said, what method can do a better job at predicting this? We started with the phase field fracture model with just 2 parameters, right? So we wanted to calibrate the fracture strength, and we wanted to calibrate the cohesive strength or length scale. They're dependent. And in Abacus, along with my collaborator Emilio, we started developing, regular Abacus type meshes where you put the notch, you expect where the crack will propagate, you refine. But this is cumbersome, right? You have to manually refine it, and then you have to put more degrees of freedom than they're probably necessary to model this problem. And so you have 14,000, 11,000 elements in this. In the 3D case, you go to 2 million tetrahedral elements, which is a lot. And this one again takes, because it's Abacus, it's not very well parallelized. It's a code that a student wrote, right? You know all about those. And I wrote some very bad codes when I was at Northwestern. So scalability is not our motivation. Our motivation is to get some results and get a paper, right? So 2 million elements. This ran for multiple days. And then you have same old here. Whereas on our end, we have another paper with my postdoc where we started doing this adaptivity test. And this is how our method works. It only refines it wherever it's required, where the supports are, where the stress concentrations, and where the fractures are, right? And it also works in 3D. And this is all Phoenix, by the way. Phoenix has automatic mesh refinement within. So within a few lines of code, you can actually have adaptive 3D meshing in 2D and 3D. And so we got these fracture patterns at a fraction of the cost. So if you compare the 2 simulations in 2D, this is our adaptive simulation. This is our non-adaptive type, like standard, you manually refine it. And what you see is that you're able to get from 3,200 seconds to 700 seconds, 1/4 reduction in computational cost. And you're able to run this more efficiently with a smaller mesh size, and you get the same crack pattern. So then we did the validation on other experiments, and we were able to get the load displacement curve with experiments and the crack path matching. Even in 3D, we can get the load displacement curve, and then we can get even the twisted crack pattern. So there is a little bit of a mode 2 and a mode 3 in this case because of the twist of the inclined crack. So the crack surface kind of twists. So we were able to capture that very nicely with adaptive refinement. And then we did all the 4 different experiments. We were able to get good matching. The blue and the black are bounds. So if we changed the Young's modulus from one to another, we can do an upper bound and a lower bound calibration because experiments always have variability, correct? And so in all cases, we even in 3D experiments, we were able to take the X-ray tomography and we matched the experimental crack path with the numerical crack path. And we showed all views, right? So very good matching with just 2 fracture parameters. And so that's when we said the damage mechanics challenge phase field is a good option if it is brittle material, right? There are other materials which are not. So okay, I'm almost close to my time, so if I may take just 5 minutes and explain like how we are doing CNNs with damage mechanics and phase field especially. These are the 2 papers which have all the details by my PhD student who graduated recently. Our motivation was, and this was funded by 3M. So, I mean, last year I came here to give the same talk at the 3M campus in Twin Cities. So we have all these particulate composites. If we want to do finite element modeling, Then you have to have very refined meshes to do fracture propagation with these microstructures. So it's very hard. And so we said, even with phase field damage, with adaptive methods, it's still computationally intensive. So our strategy is, can we do some sort of surrogate models to extract this as a constitutive law? And then if you just did data-driven only, then you'll have problems with ML. So can we use damage as a physics information in these in this training process, right? So we generated a lot of data. We used our Phoenix software to generate lots and lots of data. So always remember that some of the CNN models that you use, they're very data hungry. That means that you need the data. Experiments always won't give you that much rich data, so you still need your FEM, right? So we cannot just throw away all the past FEM and fracture mechanics. So we generated for each case 1,000 data points using FEM with very fine meshes. We used our Phoenix adaptive codes for it. We extracted peak loads. We extracted images of damage, images of stress. And you get these information right at the point where it's peak load. Now what we are trying to understand is, if we gave this and this information to the machine learning model, can it predict the peak load with much better accuracy than if it did not, right? So instead of going from microstructure directly to peak load with a black box machine learning model, we are saying let's do microstructure to damage and damage to peak load, or microstructure to stress and stress to peak load. So that was our paper 2003 in Journal of Engineering Mechanics. And what we see is that if you start with the baseline, where you go from geometry to directly to peak load, you get a lot of scatter. The model is not very predictive. But you inform it with stress, you get a very good matching on the test data. If you inform it with damage, it's better than before, but stress information seems to make the CNN model work much better, right? And if you look at the errors, you're getting 0.6% error with reducing this. So we were pretty happy with this. And then we said, can we use this for something more design? So we said, okay, what is design, right? Design is always an inverse problem. You want something where you want a certain strength to be accepted, but for that you need to pick how your microstructure or how your structure should look. So you take the strength information, backpropagate the gradients, and try to optimize this microstructure for the strength. I'll skip the details of all the math, but this is how our optimization works. We start with some low initialized value, and then we are optimizing using the machine learning model. The peak load is increasing. Now we went from 3,000 to 4,000, and it converges, and then you have this sort of a structure that comes out of this sort of training process. Okay? And then we check that strength with FEM to say that this is correct. And then we initialize with other kinds of strengths, and then we get different type of structure, right? I'm skipping a lot of details here just to give you a flavor. And eventually what we found out is that different conditions lead to different types of fiber arrangements in microstructure. So the diamond fiber comes when you are optimizing for strength in both directions, right? And so with that I'll conclude. Sorry if I went over a little bit of time. So we have these phase field stress-based models that work well for brittle materials. We can use CNNs to do faster prediction. And any phase field model, you have to configure it well with experiments and get the parameters right to make good predictions. And then of all this, efficient methods are necessary to solve real problems at large scale. So if you walk out of this with just one takeaway, that you still need efficient finite element methods to do the problems right. Okay? So thank you for your attention, and happy to take questions.
All right, thank you. Any questions? Yes. Michael.
Thank you for your talk.
Yeah.
My question is about your part one. How do
Yeah.
you consider the temperature change? Or like when you are simulating, do you also consider some part of ice melting in your crevices?
Yeah, so in these cases, it's a fictitious case, right? So we have hydrofracture here, but we don't have any thermal effects. So it's just the pressure that the water applies in the fracture is causing it to propagate. In a different paper, we add melting to it, and we realize that if the ice is less than minus 7 degrees, that means ice is always below zero, right? So if the ice is very, very cold, like minus 7 degrees or colder, the water will actually freeze in the crack and it will heal, right? But if it's above that temperature, then the melting is not strong, the melting is not strong enough to propagate the cracks, but the freezing is not strong enough to stop it, so you still get cracks. So that means that if we are modeling ice at above minus 5 degrees, then you can ignore thermal effects and only model the hydraulic effects. Yeah, very great question. Yeah.
Yeah, thank you. Actually, I want to follow this question. Just a general question for the phase field model, how to generally consider the thermal effect and the viscosity effect into the phase field model, because you need to formulate the potential functional.
Yeah.
The second question is regarding the adaptivity. I want to know what kind of criterion you will use. Is it that specific to the fracture problem you are looking at?
Okay.
Yeah.
I'll come back to your second question. I have some clarification to ask. So going back to thermal and viscous, how do you incorporate them, right? I don't have the equations in this slide, but the way we model that is, so you have this potential energy, correct? And here I only incorporated the standard linear elastic energy. But you can say that this is not the full strain, but only the elastic part of the strain. And then you can assume that it's small deformations, but large rotations, right? And you can still formulate it as additive decomposition. So you have the total strain is equal to the elastic strain and the viscous strain. Only the elastic strains contribute to the strain energy. The viscous strains don't contribute to the opening of the fracture. They go into a different, separate dissipation process. And so when you do that, you can incorporate viscous effects in some way into that. So that's what we did in our engineering fracture mechanics paper, 2022. We did this additive split. Then thermal effects can also be done in a similar way. The only way we incorporate thermal effects is we have a thermal strain, right? So alpha, which is the linear coefficient of thermal expansion, you can incorporate in it, and then you get thermomechanical type stresses. But if you're trying to do melting, then you have to do more kinematics. So what you're saying is, let's say you have a crack. The crack opening is not just related to the stress, it's also related to amount of melting. So the crack separation, if you look at it in a cohesive zone modeling setting, has two components. One has the elastic opening, and one has the melting based opening. So you have to subtract those and take care of it, right? So it can be framed into this phase field fracture approach and done that. And then in phase field, one of the difficulties is how do you define crack opening? And that problem has been solved with a couple of papers. DeBorst and Tim Hochman did that along with Jinghan Chu at KAIST. And they use an integral to extract what is the crack opening, and then they used it for hydraulic fracture. So you can do those, but these are recent advances, right? And then you said the second part, activation or?
The adaptivity, the machine, what criterion?
Oh, adaptivity, yeah. So that's a very important point, right? So adaptivity, we have all these criterion here that I show. For each of that, there is a estimator and an indicator. So we take a certain value of the strain energy increment, normalize it with respect to the strain energy release rate, critical strain energy release rate. Then we choose a number between 0 and 1, and then we say that if it is greater than that, then we divide the element. And then when we are dividing the element, we will only do it with one H refinement. That means that in every case, you have a triangle, you make it into either 4 like that or 2, right? And so we either half the mesh size or we divide it into 4 smaller triangles. And when we are doing this, I'll play this one here, right? So if you see here, always the yellow is next to a green, the blue is next to a green, right? And what that means is that neighboring elements can only have one order of polynomial degree difference. That means 6 must be surrounded by 5 order, 4 must be surrounded by 5 order, and so forth, like, right? So, or maybe I misspoke, like the 5 is the green, 6 is yellow, right? So I said it the other way. So you have to put all these engineering criterion in there to make these work. So there's a lot of trial and error. It's more of an art than like, solid criterion. Yeah, thank you.
Thanks. Just a really quick question. I know very little about glaciers calving, but what's the temporal scale? And I'm wondering how well do your models predict that temporal scale? Because I imagine that matters a lot as well if you're trying to predict when this will happen.
So I'll quickly go to this. That's a very good question, actually. That's one of the things that models don't do very well, because if you do linear elastic fracture mechanics, there is no time, right? It's just a quasi-static process. And so in this case, if you see, there is 2.2 years here. That means from the time that the crack initiated here, there's already a big crack, but then it took 2 years to go from that initial crack to the full crack. When we do modeling, what we do is we assume that every crack propagation is quasi-static, but then the driving force is changing because of some other time-based event, like a viscous component. And so we are able to calibrate some viscosity and contributions that match this time very well. But it's still calibration. We are not able to predict time. Yeah, very good question. Thank you. Any more questions? Yes.
I have a question about the inverse modeling part. You mentioned about you use the differentiable programming. I'm wondering how kind of differentiable you use. You use auto differential or a trend method here to do the optimization?
Yeah. So the question is about how do we get this whole thing as a differentiable system, right? Yeah. So the simplest thing is that if you are able to define a forward problem in PyTorch, it automatically does the back propagation and gives you the auto differentiation gradients, right? So the whole point in the code is how do you define this forward problem? This one is a CNN, so it was easy. You give it an image. The way the image is, you take the image, you make it 512 by 512 pixels, right? It goes into it with a unit type architecture, And so it's going from a high resolution, low channel to a multi-channel, low resolution data. And then it's getting fed into the this, and then it gives, you train it on the strength. So this part, once you define the forward problem, you get the auto differentiation based back propagation. The thing is, how do you generate these images in a way that is also differentiable? So we start with the fiber diameter, fiber radius, and then we use level set functions along with sigmoid functions, which are differentiable, and convert it to an image. So you're basically taking a sigmoid function which says it's 1 if it's inside the fiber, 0 outside the fiber. For each fiber, you're superposing them, and then you get this function that defines this image as a differentiable thing. You give the forward problem, the auto differentiation gives you the backward. So that's how it's implemented.
Thank you.
Great question. We struggled with that initially, and then we said, okay, why don't we use sigmoids? Because if it's a step function, it's very hard for it to do the gradients. Yeah.
Okay, I think for the interest of time, we'll stop here. And let's thank our speaker again.
Yeah, thank you. Thank you very much.